Today I'm going to talk about the recent progresses on approximate homomorphic encryption and its application. And my name is Yongsoo from, and this work was started when I was in Seoul National University last year, and I'm currently in UC San Diego, and I'm going to join Microsoft Research very soon. So, I can imagine many audience are not so familiar with homomorphic encryption because it is not elliptical cryptography. So I prepared a very kind and easily understandable background. And the goal of this talk is to introduce two main features about homomorphic encryption for application. And this scheme is simply called pending for the title of the first paper in HSC. And we intended the title to have the same pronunciation as this word. So I think many of you can read this word, but I don't know how to pronounce this in Japanese, but we can say hean in Korean. And the second one is the bootstrapping of homomorphic encryption. And I conclude my presentation with some related. So in classical encryption, we just aim to protect the data by encrypting the database. But in advanced cryptography, we would like to do something more on data, not just protecting them. So we compute something on encrypted data instead of the encrypted security. So differential privacy and zero knowledge proof for multi-path computation are some typical examples of advanced cryptography. And I'm going to talk about homomorphic encryption today. This primitive is relatively very young compared to others. It has not been 10 years since Gentry first constructed the homomorphic encryption. And more formally, homomorphic encryption allows us to perform any arithmetic operation on encrypted data. So we can encrypt messages and evaluate some function on encrypted data, and its resulting ciphertext correspond to the plain value, correspond to the same computation on plain values. So this is very typical model, outsource of computation and storage of homomorphic encryption. So we have one cloud server, semi-honest server, but it could be malicious. And we have a minion. This guy is a trust party. And this minion generates a pair of public key and secret key and distributes his public key to the database owner. And database owners use this public key to encrypt their data and send it to the server. And server computes something on this encrypted data and return this outer ciphertext to the minion. And this guy can use his secret key to recover the plain value. So usually homomorphic encryption is compared to multi-path computation because multi-path computation is another way to securely compute any arithmetic between more than one parties. But in this case, so data owners should make some protocol between them, and these four participants should be honest, and none of the two cannot collude each other. So this model is somewhat more stronger than homomorphic encryption, and the communication cost of this protocol grows linearly on the size of circuit and grows very rapidly on the number of parties. So the communication cost is the main problem in the case of multi-path computation. So in summary, homomorphic encryption is good for long-term storage and reusable of the same ciphertext for different computations because the server can store just one ciphertext and reuse store the ciphertext for arbitrary computation. But in the case of multi-path computation, we should make everything new protocol for every single computation. So, and model is more strong. And homomorphic encryption is slower in computation, while multi-pass computation is slower computation. So the main bottleneck to make homomorphic encryption practical is the complexity, maybe. So I said it has not been even 10 years before first development of homomorphic encryption, but the speed of improvement is really remarkable. So it's even much faster than Moore's law. So as you see here, the first implementation of HC was done in 2011, but it took almost 30 minutes to perform only a single bit operation together with bootstrapping. But after 2 years, the speed was improved very much. So the evaluation of AES-30, 120 blocks of AES-30 could be done in 36 hours. And after 1 year, IBM published an open source library called ACL, and the same computation could be done in only 4 minutes. And nowadays, there are a lot of different schemes with different advantages and disadvantages. And academia and industry people are publishing a lot of open source libraries, which is much more simpler and faster than the previous one. And there are, if you search homomorphic encryption on Google, you can find like 100 or 1,000 papers of applications of homomorphic encryption for many different tasks. And there have been 3 standardization meetings since last year, and we discussed about some security of LW problem and API of libraries and so on. And some benchmarks have been reported in IDES competition since 2014. I explain what it is in the following slide. Okay. So I brought some news from Christine's session in last IDES. So recently, Satya Nadella is a CEO of Microsoft. Had a talk in Microsoft Build, which is the biggest annual conference held by Microsoft. And he mentioned homomorphic encryption and the importance of training on encrypted data without information leakage. Because nowadays, big data analysis and machine learning are really hot topic, right? And to introduce some other news, IBM said IBM chose 5 main research topics in following 5 years, and homomorphic encryption, lattice cryptography is one of them. And Google is now started to service data query based on homomorphic encryption. And there are a lot of startup companies like Invel or Duality Cloud. Duality Cloud is co-founded by Shafi Goldwasser and Dino White. So let's see why it has been very practical and why these industries are really interested in homomorphic encryption technology. So currently we have 3 different kind of best performing homomorphic encryption schemes. So let's say flash correct homomorphic encryption and fast bootstrapping and approximate encryption. So first one can encrypt binary field element in a ciphertext, but it is allowed to us to pack many plain text in a single ciphertext. So for example, one ciphertext can encrypt like 10,000 finite field elements, and if you multiply it to ciphertext, then the 2 values in the first slot are multiplied, and second values in the second slot are multiplied, etc. So this computation on text ciphertext looks like a SIMD operation on hardware. So this packing method is not useful to reduce the speed of increase the speed of computation, but it is really useful when you work on very big data and reduce the amortized time. And basically, addition and multiplication on binary field are properties, and there are some libraries implementing these BGB or BFV schemes like HLib, from IBM and Jill of Microsoft Research and Palisade of Reality and so on. So in the second category, a ciphertext can encrypt only a very short string. So amortized expansion rate or amortized timing is much worse than the first one, but it can evaluate arbitrarily look a table on very small string together with bootstrapping. So we don't need to worry about like a level of ciphertext or like, and it is very easy to just general user or standard programmer to program a software using this library, but of course it is not good for expansion rates and amortization. And TFHC library is currently available, and this is written by a European team, consisting of 4 or 5 institutes. And the last one is Heian. And this one is a little bit similar to the first one, but a ciphertext can encrypt real or complex numbers in its plain text slots instead of finite field elements. And it supports 6-point operation between ciphertext, and it also supports hacking technology, as in classical HC. And so National University first published a library. And if I compare these schemes to computer hardware, I can say first, classical HC is a GPU processor supporting some discrete computation, like or insert to variables. And second one looks like a CPU processor, which can do anything on a very small memory. And last one can be compared to, again, GPU processor, but it supports some approximate computation, like a floating point or fixed point arithmetic. And I can say, of course, this third one is definitely used for many big data analysis, because in machine learning, we should deal with a really huge database, and we repeat some computation over and over on large data. So this hacking method and approximate computation are really useful. So as an example, so as I mentioned before, IDES workshop is a kind of international annual workshop together with competition. So organizers every year publish 3 main tests from biomedical area, and they ask participants to submit some cryptographic solution to solve the security and privacy issue. So a lot of the size of this conference is growing very rapidly. For example, this year more than 100 teams registered this competition, but of course only a few of them could finish the solution. And in last year's IBIS competition, organizers already noticed the importance of training of a model on encrypted data. So the test, homomorphic encryption track test was machine learning to predict the disease. So the goal is to build a model. So this is a binary classifier distinguishing some disease and healthy people from their vector. And the database size was consists of 1,500 records, and each of samples have 80 results. And this is a summary of this competition. And last year, only our team used Heian scheme, because Heian just published last year, and we won the competition, and speed and accuracy was the best among submissions. And in last year's submission was semi-parallel GWAS. This was much harder than last year's one. So instead of performing only one training here, we were asked to repeat many logic and regression training for a database looks like this. So in naive solution, we had to repeat 15 1,000 times of logistic regression training, but participants of course found a way to parallelize this test. And among more than 30 registration, only 7 teams submitted solution, and 4 of them passed the correctness test. And UCSD team was the test this time. And I'm excited to see that in this year, every team partially or fully used the hand scheme, but each of team implemented the same scheme on their own package, like Palisade or ACLab and so on. So now this scheme was implemented separately by NS5 teams. And as a source of advertisement, Microsoft Research recently released a new version of C library, and now it's support for the implementation of hand scheme as well. So, okay, now it's time to go into the details of the paper. So, the idea of hand is that in computer system, of course, we cannot exactly store the real number on computer system. So what you're doing is to storing on your finitely many digits of a certain real number. So for example, to store a scale of 2, we multiply 1,000. Here 1,000 is a scaling vector and round it to the nearest integer. So we remember this number 1412 together with scaling vector 1,000 to represent this scale of 2 on computer system. This is what we are doing now. And for computation, we first multiply these 2 integers and then extract its most significant digit to maintain the size of numbers. So here the rounding operation is really important to make a trade-off between precision and performance. So as an example, when you multiply these numbers, on computer system we store these 4-digit integers together with this scaling number. So we first multiply these significant digits and extract the most 4 digits of result to maintain this scaling vector and the size of number. So the problem is that most of actually all of lattice-based homomorphic encryption cryptography is based on learning in error protocol. This is suggested by Legev in 2005, who awarded this year's Nobel Prize. And in this problem, LW sample is a vector consisting of a scalar V and vector A, such that whose inner product with a secret vector is approximately equal to 0 modulo Q. So roughly speaking, the linear system with a small error is very difficult to solve. So in previous homomorphic encryption settings, ciphertext of a message n is a kind of LW sample whose inner product with secret vector is Q over T times m plus E modulo Q. So this is approximately equal to Q over T times m. Here Q over T is a kind of scaling vector. So this picture is visualizing this encoding. So right side is least significant of bits of modulo Q, and left hand side is the most significant bits. So m is placed by here with a scaling vector Q over T, and E is placed in these significant bits. And we should have many zeros, empty space between this message and error. Otherwise, message is destroyed by the LW error from LW. So basically, previous HC scheme supported modulo T plain text because M was stored in this modulo T space. But the problem is that modulo T plain text is not compatible to this rounding operation. Rounding operation is not easy to represent as a polynomial over modulo T. So that was a difficult test for 4 years. So our idea is very simple. So our encoding is P times M plus E, where P is a scaling vector. So in the case of ham, encryption of m is a vector whose inner product equals to p times m plus e modulo q. So here, p is much smaller than q. So this is approximate value of p times of m. So previously, error was fully separated from message, but now we consider this error of AW as a part of message, because in practice, every computation introduces additional error during approximate computation. So it is fine, even though we have some additional error, as long as this error is small enough not to destroy a significant digit of encrypted message. So, and for homomorphic encryption, for homomorphic operation, if we have two encodings of M1 and M2, then if we add mu1 plus mu2, then it returns us to an approximate value of p times M1 plus M2. And in the case of multiplication, if we multiply these two approximate values of p times mi, then resulting ciphertext includes mu1 times mu2, which is an approximate value of m1 times m2 is scaling factor p squared, not p. So we should find a way to recover the scaling factor p as we did in plain computation. But luckily, we could adapt some existing technique for the modular switching. So it is able to transform this ciphertext into a ciphertext with a smaller modular q over p, increasing increasing mu divided by p, which is a approximate value of p times of m1 times of m2 as we desire. So now we almost mimic the fixed point arithmetic over homomorphic encryption crypto system, and this is a kind of level homomorphic encryption because ciphertext modulus should be a power of, because ciphertext modulus is divided by p factor each of the multiplication. So ciphertext modulus is p to the L, where L is the maximal depth of a circuit to be evaluated. So I briefly explained the basic idea, but of course it is very important to support hacking technology to encrypt a big amount of database in a single ciphertext. So usually we use this ring structure and a ring variant of LW problem called ring LWE. So here we use this cyclotomic polynomial of how to degree, and ciphertext, the scheme is constructed over this modulo Q cyclotomic polynomial. And as I said, our goal is to encrypt a vector into a single ciphertext instead of a single value. So the idea is that basically our scheme can encrypt a single polynomial in this cyclotomic ring. And we note that this polynomial is factored into linear polynomials in complex space. It has n over 2 roots from zeta 1 to zeta n over 2, and their inverse or conjugate are also roots of this polynomial. So what we are doing for packing is that we consider this space as a subring of this continuous cyclotomic polynomial, and this space is actually isomorphic to this space, the n over 2 tuple of complex values. So the decoding method is done by evaluating this zeta from zeta 1 to zeta n over 2 to the polynomial m. So if you'd like to encrypt a vector of complex numbers, then you should first recover this m of x, which is the inverse of this Fourier transformation, and use this polynomial to encrypt, use our scheme to encrypt this polynomial. So as a very small example, when n is 4, we we can choose these two roots, which are eighth root of unity. And for encoding of this complex vector, we first run Fourier transformation to find this polynomial. So if you evaluate zeta1 and zeta2 at this polynomial, you will have these two values. And then this polynomial is not still an integral polynomial, so we multiply a scaling factor, as I explained before. So let's say 1000, and round it to the nearest integral polynomial, which is 2000 minus 2820, blah blah. And you can confirm that if you evaluate zeta1 and zeta2 at this polynomial, then the resulting value is really close to the 1000 times of this zeta, as we said. So if you multiply two polynomials using the Heian scheme, then inside the plain text, the numbers are multiplied one by one. So in summary, Heian natively support for the fixed point approximate fixed point arithmetic, and ciphertext modulus should be L times log P. Here L is a depth of circuit and log P is a precision of numbers. And it is very useful to evaluate some analytic functions like polynomials or multiplicative inverse, trigonometric functions like sine or cosine, and exponential functions or some logistic function or sigmoid functions usually used in machine learning analysis. And it supports for SIMD operation. And I didn't explain this part, but it is able to compute some permutation on encrypted data without decryption based on this rotation arithmetic. So we can shift this vector to get the encryption of this Z prime from the encryption of Z. So, okay, let's move to the next paper. This is about bootstrapping of approximate homomorphic encryption. So, as I explained before, our scheme is level. So each of the ciphertext has its own level, and the level decreases as the computation progresses. So finally, if ciphertext level reaches down to the lowest level, we cannot perform any more computation. So there should be a way to refresh your ciphertext to perform further computation again. So the idea is from Gentry in 2009. Simply speaking, it is done by evaluating the decryption circuit homomorphically on ciphertext. To be precise, we are given a ciphertext. Let's say this is a lower level ciphertext, and this is a decryption formula. So decryption algorithm is public, but we need secret key to recover this encrypted message. And this formula is equivalent to this formula, where F is a circuit taking secret key as an input and outputting the message M here. So for a given ciphertext, this circuit F sub CT is public, and we don't know about this secret key. So in the case of bootstrapping, homomorphic encryption scheme publish encryption of secret key encrypted by itself. So the purpose of this is that if we evaluate this circuit, so this circuit is public circuit for a given ciphertext, and this bootstrapping key is an encryption of secret key. So from the homomorphic property of homomorphic encryption, evaluation of circuit on encrypted data is correspond to encryption of this computation on plain value. And you can see that this is M. So the output ciphertext is again encryption of M. So the input ciphertext CT is encryption of M, and also the output ciphertext is encryption of M. But difference of these two ciphertexts is that this ciphertext has a very low level. So it is not allowed to perform more computation. But here, this encryption bootstrapping key is a kind of fresh ciphertext. So this output ciphertext is not placed in the lowest level. So it is somewhat fresh ciphertext, which we can perform more computation on it. But one problem over here is that every computation in Heian is a kind of approximate computation. So if we just follow this framework, then the resulting ciphertext encrypt n plus e instead of n. But there is no way to extract or cancel out this error. But again, it is fine as long as this e is very small, so that the significant digit of this encrypted message is preserved. So we have a little bit different notion of bootstrapping, but technically it's doing the same evaluation of the decryption circuit. So now our goal is reduced to this problem, how to evaluate the decryption circuit. And the decryption of Heian is represented by this inner product and this modular Q operation. So since our scheme supports linear arithmetic, this part is fine. It's just a linear arithmetic. But here, modular Q operation is problematic because our scheme performs approximate arithmetic over real number or complex numbers, and this modular Q operation is not such approximate arithmetic. So our goal is to perform this modular Q operation. The modular Q function is identity nearby origin, and it is a periodic function with period Q. So it is easy to perform inner product. So our goal is to extract this mu part from T, which is a mu plus a multiple of Q. So the naive solution is to use, for example, polynomial interpolation to represent this modular Q operation as a polynomial over the real numbers. But the problem is that this is not continuous function. So any approximation of any polynomial approximation of this function fails because we have a jump here. So the first idea is to restrict the domain. So we assume that the encrypted message is relatively smaller than the size of modulus, ciphertext modulus. So now our target function looks like this, pair piecewise linear function. And second idea is to make approximation of this function using sign function. So if this message is small enough compared to hypertext modulus, then this sign function is really effectively approximate this function. But still, this sign function is not a polynomial, but it's analytic. So the next goal is to approximately evaluate this sign function using polynomial approximation. So this is the sign function we want to approximate. And the naive method is, again, direct Taylor approximation. But the problem is that to guarantee the precision and accuracy of approximation, the depth of degree of Taylor polynomial should be very huge. And the Taylor polynomial is not stable in numerical sense. And this red curve is a graph of Taylor polynomial of degree 31. It fails to approximate sign function very quickly. So the second idea is to consider some recursive way to evaluate this sign function. So we first consider the very low degree polynomial approximation of these two functions, cosine theta over 2 to the r and sine of theta divided by 2 to the r for some r. Here r is a, so this is a sine function, but whose period is 256 times longer than this target function. So it looks like an almost line. So it is very effectively approximated by a small degree Taylor polynomial. And what you do in the next phase is to use this double-angle formula. So if C sub k and S sub k are good approximation of cosine and sine, then this C sub k plus 1 and S sub k plus 1 are good approximation of cosine and sine with double angle. So, and we just repeat many times, 8 times here. And you can see that the final result is perfectly fitting to this target function phi. So what we are doing here is that we just evaluate very small degree polynomial first and repeat the evaluation of this double angle formula r times to get a very effective approximation of sine function. So advantage of this method is that this computation is very numerically stable. So here numerically stable means that if you have you can think about overflow in fixed point arithmetic, for example. If you compute Taylor approximation, then you should compute like a 31 factorial, which is huge. And the division between huge values sometimes lose precision in practice. But in this case, we just square ciphertext and multiply ciphertext. We don't have any overflow or any tiny or huge values. So this is very numerically stable. So that's why we got a really high precision after computation. And the complexity of this arithmetic is grows linearly with the depth of circuit, because this one iteration requires only 2 multiplications. And but unfortunately, in the case of ring-based Heian, we need more idea, because as I said, homomorphic operations are performed on plain text slot, not on coefficient. But in our ring-based scheme, our goal is to recover mu of x from a ciphertext encrypting q times I of x plus mu x. So we need to perform modulo q operation on coefficient, not on plain text slots. So there should be pre and post computation before and after modulo q operation. So first step is to transform this ciphertext to another one, which encrypts the coefficient of this input ciphertext inside of its plain text slot. So these two ciphertexts are not the same. It requires a huge computation. And the second step is sign evaluation, what I explained before. And the final step is to recover the location of this value. So we need to generate ciphertext encrypting mu x, whose coefficients are T modulo Q. So basically, if I summarize the performance of bootstrapping, that basically depends on the evaluation of sine function. But however, complexity of bootstrapping relies on the complexity of this pre and post computation, because this part can be done very quickly. So as an experimental result, we consumed like more than 100 seconds for these two linear transformation steps, and only 12 seconds for sign evaluation when working on 128 slots. Each of them has 12 bits precision. So there were some open questions here, and recently I solved this problem with Howard and Elaria in Microsoft Research, and we somehow optimized this linear transformation procedure using some FFT-like algorithm, and suggest another method of sign evaluation using Chebyshev approximation. This is another efficient way of evaluation of sign, and is also numerically stable. And let me introduce a few more related work. One example is that recently we evaluated encrypted convolution neural network on encrypted data using AI, and recently these papers, I'm not involved in these papers, but there are two papers from Microsoft and Intel, which supports some user-friendly AT compiler for deep learning. And recently we published a paper to optimize the evaluation of a GAN scheme. So now our library is working without any high precision arithmetic library, like NTL or GMP. And this library was used in ITS competition this year. And we have another paper for GAN over the real numbers instead of complex values. So thank you for your attention. Our scheme is basically based on the hardness of ring-and-W problem, and I'm not an expert of script analysis, but there have been several papers to estimate the script of AW programs. So, for example, Martin address is servicing the AW estimator publicly, and it was included as a part of standardization to estimate the script. And now many homomorphic encryption research teams are using the same standard, same parameter set to estimate, guarantee the same script. So we are just following the system.
More questions? How it works? Yes.
Could you show me some benchmark result of your new bootstrap?
Yeah, so now the paper is available on ePrint, but I didn't prepare the slides, but I can, as I remember, when you set the same number of slots and the same precision, the performance was improved by almost 100 times, for example. So here, the timing. So basically, improvement was done on this linear transformation step. So here we took 127 seconds in previous paper, but now it can be done in just a few seconds. So a few seconds. So so you can see the numbers on ePrint. I don't remember, sorry.
What is the security parameter?
On the same security parameters. So this improvement was made by modifying the algorithm and improving the speed of basic implementation. So it has both engineering contribution and theory.
No questions? The same speaker again?